introduce myself, Dilip Udani, Assistant Professor at LJ Institute of Engineering and Technology. We have started this unit, that is ODE of higher order. ODE means ordinary differential equation. And we have seen two cases of this topic, that is homogeneous linear ordinary differential equations of higher order with constant coefficient. Today we will see case number 3 and case number 4. So let's start. So first of all, we will see general solution of homogeneous linear ordinary differential equation of higher order with constant coefficient. And first of all, we are going to discuss case number 3. Now, what is case 3? If we will get complex roots, complex roots. If you will get the values of m1 as alpha plus I beta and m2 as alpha minus I beta, and remaining n minus 2 roots as real and distinct value, say m3, m4 up to mn. So in this case, how will you write down the general solution? That is y equals to c1 e raised to alpha x cos beta x, c2 e raised to alpha x sin beta x. It means for complex conjugate pair alpha plus minus I beta, we will write down c1 e raised to alpha x cos beta x plus c2 e raised to alpha x sin beta x. And for remaining roots, for m3 we will write down c3 e raised to m3x plus c4 e raised to m4x plus dash 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 plus cn e raised to mnx. This is how we will write down the general solution when the roots are complex and real roots. Here we have considered m1 and m2 as complex conjugate pair roots and m3, m4 up to mn as real roots. Now I will make you understand this concept with the help of example. Here the given differential equation is d cube plus 1y equals to 0. So f of d is d cube plus 1. So to solve this differential equation, we will write down f of d equals to 0 and we will replace b by m. So we have f of m equals to 0. Now to evaluate f of m, we will just replace d by m in f of d. So we have m cube plus 1, that is equals to 0. Now we will factorize this equation, m cube plus 1 equals to 0. Now how will you factorize? So for that purpose you have to remember this formula, that is a cube plus b cube, a plus b in one bracket, a square minus ab plus b square in second bracket. So we will apply this concept on m cube plus 1. So we have m plus 1 in one bracket, m square minus n plus 1 equals to 0. Now we will equate these two factors to 0. So we have m plus 1 equals to 0, m square minus n plus 1 equals to 0. So from m plus 1 equals to 0, we have m equals to minus 1. Now to factorize this equation, m square minus m plus 1 equals to 0, we will apply the concept of delta method, that is m equals to minus b plus minus square root of b square minus 4ac divided by 2a. Now what is the value of the a and c? Here the coefficient of m square is 1, so the value of a is 1. The coefficient of m is minus 1, so the value of b is minus 1, and the constant term is 1, so the value of c is 1. Now minus sign will be as it is, replacing b by minus 1 plus minus square root of b square. B is minus 1 and its square is 1. Then after minus, and if you replace a and c by 1 and if you multiply it by 4, you will get 4, and divided by 2a, if you replace a by 1 and if you multiply it by 2, you will get 2. So we have minus minus plus, then after plus minus 1 minus 4, that is minus 3, and minus 3, that is nothing but 3 into minus 1, and minus 1 is I square, that is complex number iota, and divided by 2. Now m equals to minus 1 and m equals to 1 plus minus root 3I over 2, dividing this one by 2 and this root 3 by 2. So we are getting one real value and one complex conjugate pair. So how we will write down the general solution? So that is y equals to, for this minus 1, we will write down c1 e raised to minus 1x plus, now for 1 by 2 plus minus root 3 by 2. The real part is 1 by 2 and the imaginary part is root 3 by 2. Alpha is 1 by 2 and beta is root 3 by 2. So in this case, we will write down C2 e raised to 1 by 2x cos root 3 by 2x, then after plus C3 e raised to 1 by 2x sine root 3 by 2x. So this is the required general solution of the given differential equation, that is b cube plus 1y equals to 0. Now we will see case number 4, general solution of a homogeneous linear ordinary differential equation of higher order with constant coefficient. Case number 4. And what is that? That is repeated complex conjugate roots. Along with repeated complex conjugate roots, we will be having real values also. Say we have one pair alpha plus minus I beta, second pair alpha plus minus I beta. Say these two complex conjugate roots are repeated, and say this value is m1 and this value is m2, and along with that we have n minus 4 roots as m5 and 6 up to mn in this way. So in this way, how will you write down the general solution? So that is y equals to c1 for the first root alpha plus minus I beta e raised to alpha x cos beta x plus c2 e raised to alpha x sine beta x. Now for the next root alpha plus minus I beta, as it is repeated, what we will do, we will just multiply by x. So we will write down c3 x e raised to alpha x cos beta x plus c4 x e raised to alpha x sine beta x plus c5 e raised to m5x plus c6 e raised to n6x plus dash 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 plus cn e raised to mnx. This is how we will write down the general solution in case of case number 4. Now we will see one example related to this topic, that is example number 2. We have to solve this differential equation, that is d raised to 4 plus 8d square plus 16 y equals to 0. Now here f of d is d raised to 4 plus 8d square plus 16. Now to solve this differential equation, we will write down f of d equals to 0. We will just replace d by m. So we have f of m equals to 0. So f of m is replacing d by m in f of d. So we have m raised to 4 plus 8m square plus 16 equals to 0. Now to factorize this differential equation, we will split the middle term and we will find out two numbers such that their product is 16 and their addition is 8, and definitely those two numbers are 4 4 are 16 and 4 plus 4 is 8. So we will write down the first term m raised to 4 as it is, and then after splitting the middle term 8m square as plus 4m square plus 4m square plus 16, that is equals to 0. Now we will take common from these two terms and common from these two terms. If we will take common from first two terms, the common is m square. So into bracket we have m square plus 4. Now if we will take common 4 from the remaining two terms, we have m square plus 4 into bracket, and that is equals to 0. Now taking m square plus 4 common from this whole expression, so we have m square plus 4 in one bracket and m square plus 4 in another bracket. Now we will equate these two factors to 0. So we have m square plus 4 equals to 0, or second factor m square plus 4 equals to 0. So from here we have m square equals to minus 4 and m square equals to minus 4, that is nothing but 4 into minus 1, and minus 1, that is nothing but I square. So we have m square equals to 4i square. So we have m equals to plus minus 2i. So the real part is 0 and the imaginary part is 2. Now applying the same concept on this vector, you can see this is the same factor as discussed with you. So we have m square equals to minus 4 and minus 4, that is nothing but 4 into minus 1 and 4 into minus 1, that is nothing but 4i square. So we have m square equals to 4i square. So we have m equals to plus minus 2i. Now as you can see that we have repeated complex conjugate roots. So here we are in case number 4. So we have m equals to 0 plus minus 2i, m equals to 0 plus minus 2i. Now based on these values of m, we will write down the general solution, that is y equals to c1 e raised to 0x cos 2x plus c2 e raised to 0x sin 2x plus, now for second 0 plus minus 2y, we will write down c3 into x e raised to 0x cos 2x c4 x e raised to 0x sin 2x. Now as e raised to 0x is 1, we will replace e raised to 0x by 1, and from the first term, that is c1 cos 2x, and the third term c3x cos 2x, we will take cos 2x common, and from the second term and the fourth term we will take sin 2x common. So we have general solution y, that is equals to c1 plus c3x cos 2x, then after plus c2 plus c4x sin 2x. So this is the required general solution of the given differential equation. So in today's lecture, we have discussed case number 3 and case number 4 of higher order homogeneous linear ordinary differential equations with constant coefficient. So this was all about today's session. Thank you for watching this video.